Moving on to example 3, we're going to move on from the world of trig to the world of exponentials with e. We love e. All right, so we're going to start with the fourth degree Maclaurin polynomial for f of x equals e to the x. That's one of our favorites, right? E to the x, you may recall, I hope you recall, is equal to, well, it's approximately equal to, I should say. It's approximately equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on. I'm going to stop at the fourth degree because that's what it tells me to do. And then it says use that Taylor polynomial approximation to approximate e. Well, e is the same thing as e raised to the, you guessed it, 1. So I'm going to replace x with 1, and I'm going to say that e to the 1 is approximately equal to 1 plus 1 squared over 2 factorial plus 1 to the third over 3 factorial plus 1 to the fourth over 4 factorial. And that's going to give us an approximation rounded to 3 decimal points of 2.708. Okay, so that is our approximate value of e. Okay, of course, that's not the exact value of e. Some of you probably already know that e is approximately 2.718, not 0.8. But let's pretend like we don't know that, and then we're going to go ahead and find the Lagrange error bound. So let's see, this is f of x, right, on the left side, and this is the Maclaurin-Taylor polynomial p sub 4 of x, right? So this, again, over here, that's f of 1 is equal to e, and then p sub 4 of 1 is equal to that exact value that we rounded to 2.708. So if we are using p sub 4 to approximate f of 1, then we are going to look at the error r sub 4 of, you guessed it, that same x value of 1. All right, so if we want to talk about the error here, then we would say the absolute value of the fifth derivative of the function, evaluated at some mystery value z, where z is between x and c, divided by the fifth factorial, and then also multiplied that by x minus c to the fifth. In this case, x is 1 and c is 0, just like it was in my sine of x example. That's going to be raised to the fifth power. Okay, and remember what we did last time is we said, oh, that numerator had to be no bigger than 1. But that's not always going to be the case, right? That was because it was a trig function, and sines and cosines are always oscillating between 1 and negative 1. What is the fifth derivative of this function? Well, that's one of the easiest questions I could ask, because e to the x differentiates to e to the x. So that's the first derivative, and then if you take the derivative again, oh, you get e to the x, and if you take the derivative again, oh, right, you get e to the x. So anytime you take the derivative of e to the x, you just get e to the x back again. So that fifth derivative is e to the x. All right, and we're trying to maximize this on the interval 0 to 1, right? Because x is equal to 1 in this problem, and c is equal to 0. Well, we know that e to the x is an exponential graph, is growing exponentially. So the biggest this is ever going to be is when x equals 1. So if I let z equal to 1 here, then that's going to give us an output of e, or e to the 1, right? Now, I don't really want to use e to approximate e. That might be kind of like trying to define a word by using the word itself. So what I'm going to do is I'm going to say, I know a little bit about e. It's safe to say that I know that e is some number less than 3. So an acceptable and easy approximation for the upper bound of that function, the fifth derivative evaluated between 0 and 1, is not 1. Don't put 1 in there. That's too small. But 3. 3 is a nice, easy number to work with that is definitely too big, right? So 3 is definitely too big. The maximum is definitely less than 3. So I'm going to replace that with 3, and that's going to be pretty safe, right? So we can say that this is definitely less than 3 over 5 factorial times 1 to the 5th. And when we work that out, that is not approximate. I believe that's exactly equal to 0.025. That's the error. Okay, so what we do now is we say, well, let's see, we'll subtract that from our approximation. That's going to give us our lower bound. A is going to equal our approximation minus our maximum error. Okay, and B is going to equal our approximation plus our error. That's our minimum and maximum potential values here. So 2.708 plus 0.025 gives us 2.733. And if I change that plus to a minus, I get 2.683. And we can now safely say that this is an interval within which E lies. And since we perhaps already knew that E was approximately equal to 2.718281828, and then some other numbers, then that's definitely going to fall in between those two guys right there, right? So we definitely have a lower bound and an upper bound within which E definitely lies.